So the current practice set number 10 has a couple of typos. So I just want to make sure that you have those on record. So there's a typo in problem number 2a. The function that you should have in A should be y is equal to x squared plus k over x squared. So you can change that. Then there's a problem in 3c where the differential equation is going to be y prime prime minus 3y prime plus 2y is equal to 0. And then there is a problem, there's a typo in problem 4b, which is that, the function, the initial function that you have is y is equal to c times e to the 2x minus 2x minus 1, where y of 1 is equal to 4, and y prime minus 2y minus 4x is equal to 0. Okay, so these are the typos. You still, I mean, you don't necessarily have to have tried these problems yet, but if you had and you have some mistakes like this, and this is what you need to know. Make sure that you write them down, because otherwise it's going to get confusing once you try to do those problems. All right, so I'm going to take over where we left off last time and start working from there. So last time we started talking about, so we had, Daniel. Okay, so we talked about differential equations. But really the focus of our class was to find a way in which we could model processes through differential equations. So the focus that we have had until now is on how to model given situations. Right? So we modeled population growth, we modeled restricted population growth. Then I mentioned the case of a model for a virus spread, and that's pretty much all that we did. The homework for today was to practice problem number 1 and practice set number 10. Does anybody have any questions about problem number 1 and practice set number 10? Okay, I see no raised hands and no comments in the chat, and nobody speaking out. I don't expect that much speaking out anyway. So if you don't have any questions, I'm going to move on right away to the next part. So the first part was really how to model problems. Can I see a show of hands for those of you who actually tried the problems in practice set number 10? Problem number 1 in practice set number 10. Okay. All right, so that is some hands, but not nearly enough. Okay, so you need to start practicing on this. You're gonna have a quiz from Friday to Monday, so it's gonna be important to get started on that. So the solutions for all of this are going to be posted pretty soon. I think I'll post them probably early this afternoon. But in problem number 1, it's really just a matter of setting up equations. So there's really no way of checking whether your answer is right yet, because you don't know how to solve things yet, right? So last week, what we said is a differential equation is basically an equation in which you have an unknown function, and its derivatives, right? So that was what a differential equation was. And what we're going to start doing today is we're going to start talking about what it means to be a solution of a differential equation, right? So what does it mean to be a solution of a differential equation, right? And so over here, what I'm going to do is start with an easy example, okay? So the idea here usual, is that if you have something that is a solution, then it should be something that once you plug it into the equation is still true, right? So for example, you can say that x equals 2 is a solution of x squared minus 4 is equal to 0, because when you plug it in, so if you plug into the equation, you get that 2 squared minus 4 is equal to 0. And so the equation is verified, right? So that means the left-hand side, once you plug in, is going to be equal to the right-hand side of the equation once you plug in as well, right? So the idea for differential equations is going to be exactly the same. So that means we're going to verify if something is a solution of a differential equation by trying to plug it into the equation and then seeing if the equation is still verified. Okay? So for example, I'm going to have so the following. I'm going to ask you to verify that the function y, which is equal to 4e to the minus 3x plus 1 is a solution of the differential equation of the dE and the dE over here is going to be y prime is equal to minus 3y plus 3. And so we're going to verify whether something is a solution of a given differential equation. Now, if we want to verify that something is a solution of a differential equation, the idea is going to be to use exactly the same logic as in the yellow rectangle that I have over here, which is essentially to say, if this function is a solution of this differential equation, then that means that I am going to plug in this function and I should verify that differential equation, right? So that means we're going to have that the left-hand side and the right-hand side, once I plug in, should be the same. And so I'm going to plug into the left-hand side and to the right-hand side, and then I'm going to verify that both of them are the same. So on the left-hand side, I have y prime. I'm going to plug into y prime. And if I plug in y, that means I'm going to have 4 times e to the minus 3 times x plus 1 prime. Right? And if I'm going to evaluate that, that derivative, that means I'm going to have to evaluate the derivative of the first term plus the derivative of the second term. So the derivative of the first term is going to be 4 times e to the minus 3 times x times minus 3, because the derivative of e to the negative 3x is going to be the same thing, e to the minus 3x times the derivative of the inside, which is just minus 3 in this case. And then plus 0, because, well, the derivative of a constant is just equal to 0. Right, so that means, again, if I have that the derivative of this, yeah, so then that means that this is going to be minus 12 times e to the minus 3x, like this. Show of hands for those of you who understand what I just did on the board. Okay, good. All right, so I've verified the left-hand side. Now I'm going to plug y into the right-hand side, and if I get the same thing, then that means that for this particular choice of y, the left-hand side and the right-hand side are the same, which means that this particular choice of y is a solution of the differential equation that I have. it's a solution to the differential equation, means it makes both sides equal. Right? So that means I'm going to have minus 3 times y plus 3. And this is going to be equal to minus 3 times 4e to the minus 3x plus 1 plus 3, which is equal to minus 3 times 4 is minus 12, e to the minus 3x, minus 3 plus 3. These two cancel out, and I get that my right-hand side is actually just negative 12 e to the minus 3x, which just happens to be exactly the same thing that I had over here, right? So these two things are equal to one another, right? So that means the left-hand side and the right-hand side for this case are equal to one another, which means that y is a solution of the equation. Is a solution of this equation over here, which I'm going to just write as a star like this. Okay, do I have any questions? Is this okay for everybody? Marcia, I think you forgot your hand up again. All right, so if there's no questions, I'm going to give you a problem and then 3 minutes to solve it. So in the next problem, I'm going to ask you to show that every function of the form y, which is equal to some constant times e to the minus x squared, where c is a constant, c is a constant, and it can be any constant, 2 minus 3, 4 minus 5, whatever it is a solution of the differential equation and the differential equation is going to be y prime, which is equal to minus 2 times x times y. Okay, so same thing. You're going to verify that this type of function, c times e to the minus x squared, is a solution of the differential equation y prime equals to negative 2x times y. 2 minutes for this. So you might realize that the constant c that I found over here can take any possible value. It could be 3, minus 2, 1, a million, minus pi, whatever you want. And no matter what the value of that constant is, this type of function is still going to be a solution of this type of equation, right? So this equation is just a single equation. And what we found is a family of solutions or an infinite amount of solutions, right? Because we have infinitely many possible values for c, and for each one of those, we're going to have that this is also a solution to the equation that we have. So what we found over here is a family of solutions. And the idea behind why this is a family of solutions and not a single solution is the same idea that we had completely at the beginning of the semester, which is that if I'm given how a function is changing or the derivative of a function, I am able to find the type of function that I should be looking at, but I don't know necessarily the one function that I'm looking for, right? So That's the whole thing where we said, okay, if I know the derivative of a function, I might know that my function looks like this, but I don't know which of these I'm going to be talking about. Okay? And so in order to find that solution, that one solution that we want, we always need to introduce an extra piece of information, which we usually call an initial condition. So the solution that I have over here, this family of solutions, is called a general solution to the differential equation. If on top of that I add an initial condition, then I'm going to have that my solution is not a general solution, but a particular solution. All right, so that's the definition that I'm going to introduce now. But before, let me write down what I just explained. So we can notice that the function y is equal to c times e to the minus x squared is not a single function, but rather a family of functions. Is not a unique function, but represents instead a family of functions, right? So, and this all depends on the value of the constant. Right, so we have a family of functions. And then based on this definition that we have for the family of functions, we're going to be able to determine what it means to be a solution, a general solution, or a particular solution. Does everybody understand the discussion over here about the family of functions versus a single function? Does everybody understand why this is not, who understands why this is not just one function, but rather infinitely many functions? Raise your hand. Okay, all right, that's good. So I'm going to define what a solution is in this case. We're going to say that the family of functions that verifies a differential equation, which I can denote by dE, is called the general solution of the differential equation. Okay. Then, if I want the one solution that in addition to this satisfies an initial condition, then I'm going to find the particular solution. The solution that in addition to this verifies an initial condition, I see, is called a particular solution and is unique. Okay, so, oops, that's not what I want to do. All right, so what I have is a family of functions that verifies a differential equation is called the general solution. So this is the word that I'm defining over here. Whereas the solution that additionally verifies an initial condition is called a particular solution. Okay, and so our usual procedure for finding a solution to an equation is going to be to first find the general solution and then to verify what the constant has to be in order for it to also verify the particular solution. So for the next example, I'm going to ask you to find the particular solution of the following initial value problem, right? Initial value problem. So for those of you who might not remember what an initial value problem is, this is a problem that includes both a differential equation and an initial condition, right? So what we're gonna have is the initial value problem, which is given by the differential equation y prime is equal to -2 times x times y, and then y of 0 is equal to 4. Okay, so I'm going to give you maybe 1 minute to think about this. And keep in mind that this differential equation that I just wrote is exactly the same differential equation that you had in the previous example. Okay, so maybe take 1 minute to think about what you need to do. If you want, you can start trying something, and then I'll give the solution for this. Okay, so maybe if you started thinking about this, you might have realized that we know that a function of the form, so like that a function of the form y is equal to c e to the minus x squared is a solution of the differential equation, right? So is a solution of y prime is equal to -2 times x times y. And let me be clear here, this is not necessarily something that you need to know at the top of your head. It's just because we just solved this in the previous slide, right? So we know that an equation of this form is going to be an equation of a solution to this type of equation, right? So that's the way that I know that. It's not because you need to know all of your functions with all of its derivatives and corresponding differential equations. So that means that my function, so the particular solution of this equation should be of the form y is equal to c times e to the minus x squared. Okay? So this is the form that this equation should, that this function should have. The other thing is that I need to make sure that it satisfies this initial condition. So I already know that this is the general solution of the differential equation. And what I'm trying to do is to make sure that I find the particular solution that also, in addition to satisfying the differential equation, satisfies the initial condition. So that means I'm going to make sure that y of 0 is equal to 4. Right? So I need that to be the case. I'm going to force this to be the case. I'm going to make sure that this is the case. How do I make sure that this is the case? Well, I know that y of 0 is just going to be equal to c times e to the minus 0 squared, which is equal to c times e to the 0, which is equal to c times 1, which is equal to c. Right? And this is independent. This is like, even if you forgot about this part, even if you had something like you don't necessarily need to know the first part, you know that y of 0 is given by that because you've already found the type of function that this is going to be. Now what I'm going to do is I'm going to force it to be equal to 4, right? Because I need this to be true. I'm going to force it to be equal to 4 by just making it equal to 4. And what I'm trying to find is the one value out of the infinitely many values of c that I can have, the one value that is actually going to make this function satisfy the initial condition. And the value for my constant is just going to be c is equal to 4. So that means that my constant in this particular case is equal to 4. And that means that if I want to look at a function that satisfies both the differential equation at the beginning and the initial condition, I'm going to have to make sure that my function has this form and that the constant that I have is equal to 4. So that means that y is going to be equal to 4 times e to the minus x to the power of 2. And this is going to be the solution of the initial value problem. Do I have any questions? Can I see a show of hands for those of you who understand this? All right, so we have about 15 people that claim to understand it. We're going to test that understanding. I'm going to give another problem in which you're going to have to first verify that something is an equation of is a solution of a differential equation, and then you're going to have to find the initial, the particular solution that satisfies the initial condition. So it's the same exact type of problem, but with a different function and a different equation. Right? So is everybody done writing this? Can I see show of hands of those who are not done writing? Not done writing. Okay, I'm going to move on to the next slide then. All right, so for the next example, I'm going to ask you to show that any function of the form y is equal to c times e to the minus x plus x minus 1 is a solution of the equation y prime plus y is equal to x. And find the particular solution that verifies y of 0 is equal to 0. Y of 0 is equal to 0. Okay, so you have 4 minutes for this one. All right, so we have the following equation that we want to verify. This is a solution for, and we're going to have to find a particular solution. I just read one of the suggestions in the survey that I gave, and somebody suggested that maybe I should just pick someone at random. We're going to see how that works. So based on that, the winner is Daniel. What is the first thing that we should do for this type of problem? Daniel, are you there? Daniel has nothing to do with the solution of the problem. All right, somebody's taking a break. Not working so well. All right, so maybe Obaida, what is the first thing that you think we should do for this type of problem?
Well, I put y prime is equal to c times e to the power minus x plus x times minus 1, all that prime.
C e to the minus x plus x minus 1 prime. Like that?
Yeah.
And then what is the derivative of this?
So that would be c times e to the power minus x times minus x
times minus x
plus 1.
Plus 1. Can anybody correct the slight mistake that there's here? There's just a, I imagine it's almost just a typo. Yes, Parsa.
He has to derive minus x, I think.
Minus x prime. Yes, so this should be a derivative, right? Derivative of the inside.
Okay.
Yeah, so then we'll have that this derivative is actually going to be just minus c e to the minus x plus 1. X plus 1. And then we can plug this into y prime over here. We can also evaluate y, and then we'll check if this is equal to x. Raise your hand if this makes sense for you. All right, good. So y prime plus y is going to be equal to, the derivative here is going to be minus c e to the minus x plus 1. That's just replacing y prime. Then plus y, which is equal to c e to the minus x plus, plus x minus 1. So this is just replacing y. So this is y prime, this is y. And this is going to be equal to minus c e to the minus x plus c e to the minus x, they cancel out, plus 1 minus 1 cancel out as well. And this is equal to x, which actually verifies exactly the equation that I have over here. So that means that the equation is satisfied. Who have done something similar to this? Right. Okay, who was on the way to finding something more or less like this, but hadn't quite managed to finish? All right, that's good. So everybody's more or less on the right track. Yeah, so this is the first part in which we're verifying whether something is a solution of a differential equation. Now, for the next part, we're going to have to verify what the particular solution is going to be, right? So, Josh, did you just forget to lower your hand, or is that a question?
I just forgot to lower my hand.
All right, okay. So then we're going to verify the particular solution, which means that we're going to have to check the one solution such that y of 0 is equal to 0. And here it's important that we keep in mind that the general solution is of this form, right? So we already know that the function that satisfies this equation is going to have this form. All that we have to make sure of now is that once I evaluate it at 0, the function itself is going to be equal to 0. Okay. So by plugging into the equation, I'm going to get that y of 0 is equal to c times e to the 0 plus 0 minus 1, which means that this is c times e to the 0, which is 1. This is c minus 1. Now, I did this, again, independently of this value. This value I haven't used yet. Now I'm going to force it. So now I need to make sure that I force this equation. I'm going to make it be true. So I have c minus 1 is now equal to 0, which means that c is going to be equal to 1. Right? And what this tells me is that if I want to have a function that is a solution not only of the differential equation that I have here, but also of the initial condition that I was given here, then my function needs to be equal to y has to be equal to 1 times e to the minus x, which is just e to the minus x plus x minus 1. And so this is the solution that I have for my equation. And this is a particular solution because it satisfies both the differential equation and the initial condition. Can I see a show of hands of those of you who understand the whole problem? Okay. All right, so I'll give you 5 minutes to rest. Probably stand up from your chairs, go get a snack or some water if you need to. If you have any questions that, like anything that you haven't understood just yet, now's the time to ask me, and then I'll keep going with the material. All right, so this is for problem number 2a. We are trying to plug in y into our equation, which means we start by plugging it into dy over dx, which means we're going to have to differentiate it. And then plus 2 times y, which is 2 times x squared, plus k over x squared. And we're going to see if we can get this to simplify. So first, we're going to have x, and we're still going to have to differentiate this term, which is going to be 2x, and then k x to the negative k over x squared is the same as k times x to the negative 2. So when I differentiate that, it should be minus 2k x to the negative 3. And so minus 2k, and then x to the negative 3, which is the same as x to the power of 3 at the denominator. Show of hands for those of you who understand that. All right. Is there anybody that, everybody lowered their hands. Is there anybody that doesn't understand how I got to this term? Okay. All right, so there's a couple of people. So essentially what I'm doing is differentiating both of these terms, right? So I have the derivative of x squared is just going to be 2 times x, and the derivative of k over x squared is the derivative of k times x to the negative 2, which once I differentiate is going to be minus 2k x to the negative 3. And what I've done is I've just written it in its simplified form right away. Okay, so then this will be minus 2 times k, and then x to the negative 3 becomes 1 over x to the power of 3. And then all that I've done is, once again, every time I'm just replacing y prime, so like here, y over dx, that just means y prime over here. And this is the same term that I've replaced over here. Okay? Whereas the second term, which is just y, this is going to be just y over here, which is going to be just y over here. Okay. Now I'm just going to try to simplify, which means that I'm going to get 2x squared. And then, so I'm just distributing the x onto both terms. And then minus 2 times k. And instead of having x at the numerator and at the denominator, I know that there's already one of the 3 x's at the denominator that is going to cancel out. Right? So that means over here over x squared. Parsa, was that your question? There seemed to be a question there.
No. I realized what my mistake was.
Okay. All right. And then you'll have plus, and here again I'm going to distribute. And you have 2x squared plus 2 times k over x to the power of 2. And lucky for us, you see this cancels out with that, and I get that my solution over here is going to be 4x to the power of 2. Show of hands for those of you who understand. Okay, you can lower your hands. Now I want to see if there's anybody that did not understand. Can you please raise your hand if you don't understand? Okay, John, I see you have raised your hand. Is there anything in particular that doesn't really make sense to you? Oh. Okay.
Yeah,
What's
I
up?
don't know where the K came from.
Okay, so this is one of the corrections that I made. So at the beginning, there's a typo in the problem set.
Okay,
which,
yeah, that's it. Yeah,
that's all. Yeah.
thank you.
Yeah, no problem. Okay, any other questions? Is there anything else that anybody here does not understand? Aaron, do you still have your hand up? I'm not sure if that's a mistake. Okay. All right, so then that means I have left-hand side is equal to the right-hand side, and this is actually a solution to my problem. John, even if you didn't have k, the equation should have been verified, right? Because this should be this should be the case for any value of k. So even if k was equal to 1, then the solution should have been verified. It's just a matter of here, like we want to do it in the more general case. Okay, so that means that y, which is equal to x squared plus k over x squared, is the general solution of the differential equation x times dy over dx, which is the same as x times y prime, plus 2 times y which is equal to 4x squared. Okay. In problem number B, you have to, in problem number 2B, you have to actually find the solution that both satisfies this differential equation and satisfies an initial condition. So you're given, in addition to this, an initial condition that your equation has to satisfy. So this is the first thing. I have my differential equation. Oops. I want to highlight this. So this is my differential equation. And now I'm going to have an initial condition, which is that y of 1 is equal to 4. And so this is the second thing that I need to make sure is verified by whatever equation I'm going to have to solve. So I have differential equation, initial condition, which makes an initial value problem. Now, I know that the solution has to be of the form, x squared plus k over x squared. So that means that y of 1 is going to be 1 squared plus k over 1 squared. That means that I'm going to have that y of 1 is going to be equal to 1 plus k. Okay. And at this point, still, I haven't used the initial condition yet. I've just plugged into the solution that I already know is going to be a solution of the differential equation. Now what I have to do is make this equal, force it to be equal to the number 4. So I just set the equation and then I solve the equation, right? So I fix the equation to be true and then I'm finding the value of k that makes this equation be true. And so that means that over here, if 1 plus k is equal to 4, then that means that k has to be equal to 3. And that tells me that the equation is going to be satisfied by a function of this form where k is equal to 3. Right, so I'll have y, which is going to be x squared plus 3 over x squared, because k is equal to 3, is the particular solution of this initial value problem. Okay. Can you please raise your hand if you understand what I just said? Okay, that's good. All right, so for problems number 2, 3, and 4, the idea is exactly the same. We're going to have a solution. You're going to have to verify that that's a solution of the differential equation. And then in problem number 4, you're going to have to also find the particular solution that in addition to this satisfies the initial condition. All right, so let me just list those things. So I'm going to start talking about the next part that we're going to be solving in this problem. I mean, I said half an hour, it's been 25 minutes. I think this is fairly okay. That way we'll get a little bit more ahead on what we need to do and you'll have enough material to study at home. So by tomorrow, you should definitely practice problems 2 through 4, and I'll take questions about those problems at the beginning of class. So far, what we've done is we know how to verify that a function is a solution of a differential equation. Right? So we know that we just have to plug in the function into the equation, and if both of the sides are the same as in the differential equation that we're given, then we're going to have a solution to the differential equation. The next thing that we knew how to do is to determine, so given the general solution, we have a way of finding whether there is a particular solution that satisfies a given initial condition. So given the general solution, we can find the particular solution that satisfies an initial condition. Right, so we just set an equation and then we try to solve that equation. So that's what we've done with differential equations until now. The problem is that all of this relies on us knowing what the general solution is. Right? So we know how to do these things. So if you give me the general solution, I can first verify that it is a solution, and then I can find the particular solution that also satisfies an initial condition. But all of this depends on knowing what the general solution is. And so the main question that I'm going to have over here is, okay, well then how do I find the general solution if I only have the differential equation? Right? Because if I only have the differential equation, which is the case for all of the problems that we modeled last class, then that means we don't really know what the solution is. That's the whole point. We're trying to find what the solution is. So over here, the question that I'm trying to answer is, okay, now if you give me a differential equation, is it possible for me to find the solution of that differential equation based only on the differential equation that I have? How do I solve that differential equation? All right, so this is the problem that I have. I'm going to start with an example. And I just want to introduce that example to kind of just dip our toes in how we're going to be solving this type of problem, but I will elaborate on it tomorrow. So I'm going to draw. And we're going to start with the same example that we talked about last time. So example. Last time we talked about unrestricted growth. And we said that when we have unrestricted growth, we said this was good for, yes, Parsa, there's a question?
Nope, sorry.
Okay, it's fine. So for unrestricted growth, okay, Megan also realized, okay. So for unrestricted growth, we said the derivative of the size of the population, so the rate of change of the population with respect to time was proportional to the size of the population. Right, so this was the model that we created. That's all that we knew how to do. Now, just for this case, I'm going to suppose that K is equal to 1, and maybe to 2. Yeah. So that we're going to have that the derivative of P with respect to T is equal to 2 times P. Or equivalently, what we have is that the derivative of the function P that gives me the population as a function of time is going to be 2 times the original function that I have. All right, so this is just a model of unrestricted growth when we have that K is equal to 2. This is just an example. We're going to see how we can start solving this type of problem. But before we start solving the problem, I want to ask you if there's any of you that would make an informed guess about what the function P has to be. So over here we have. Let me read this out loud for you, and hopefully this will help. The function P has a derivative. So I have a function P, and when I differentiate that function P, I get the same function that I originally had, but multiplied by 2. Okay, so I have a function whose derivative is 2 times itself. And so if I differentiate this function, I get the same function that I originally had, except I have now multiplied it by 2. What I want to ask you here is, does anybody have an informed guess about what my function P of T should be equal to? I'll let you think a little bit. a function whose derivative is itself multiplied by 2. Okay, so I have options. I have p to the power of 2. I have t to the power of 2. So remember, I'm trying to look for a function p of t, which is equal to this, and p of t, which is equal to this. Let's see what happens in both of these cases. Well, the first thing is p of t cannot be equal to p squared, right? Because if I do the derivative of this thing on this right-hand side, I'm going to have 2 times p, and remember, p is a function of t, so I would have to do times the derivative of the inside. So this is not actually working, right? This is not just 2 times p. What I'm trying to do over here is to say the derivative of a given function is 2 times itself, right? So I have a function. When you differentiate it, you get the same function times 2. Let's see. If I have p of t is equal to t squared, then that means that p prime of t is equal to 2 times t. Now, 2 times t is not 2 times p, right? If I had 2 times p of t, I would have that this is 2 times t squared, and these two are not the same, right? So this is also not going to work. Let me again emphasize. I'm sorry? Half the derivative. How do I take a half derivative? That's no. So when you have half of the derivative, even if you have half of the derivative over here, you won't be able to take half this power, right? It doesn't really make sense to take half the power, because then you would have to take kind of half a derivative, and that is not an obvious thing at all. It's actually like something very, very complicated. We don't do that ever. I've never seen half derivatives in my life. So we just do integer derivatives, and so this is not really going to work in this case. Let me redirect the way that you're thinking. Maybe, what is a function whose derivative is the same as the original function? A function whose derivative is the same as the original function. Yes, Barca.
X to the power of ex when it's e to the x.
Can you say the function again?
E to the x.
E to the x, okay, yes. Yeah, that's good. So e to the power of x is a function whose derivative is itself. Everybody agrees with that, right? So we have that e to the power of x is a function whose derivative is the same as itself. But now what I want is not a function whose derivative is itself, it's a function whose derivative is twice the original function. So a function that has a derivative that is the original function times 2. How could I change my function over here? It's going to look similar to maybe not e to the x, but e to the t. But I want, so like here, this gives me the derivative of e to the t is going to be just the same as the original function. I think Erin has the right idea. If I have e to the 2x or e to the 2t, I'm going to have that the derivative is going to be 2 times e to the 2t, so 2 times the original function. Well, a lot of words. So I have, if p of t is e to the 2t, then that means that p prime of t is equal to 2 times e to the 2t, which is 2 times the function p, right? So this is 2 times the function p of t. Show of hands for those of you who understand this. Okay, if there's someone that doesn't understand this, so can I see somebody that doesn't understand this? Okay. So what I have is essentially, what I'm asking you to do here is to think about a function whose derivative is twice the original function itself, right? So for example, if I think about the function e to the power of 2 times t, when I differentiate that function, I get the same derivative of the outside, so e to the power of u, and then I have to multiply by the derivative of the inside, right, which is 2. Which means that if I find the derivative of the function p, I'm going to have 2 times the same function that I started, which means that the derivative of my function is going to be 2 times the original function. Is that a little bit better? I think Lauren and Jennifer and maybe a couple other people had answered. Isn't that clear? Is this okay for everybody?
Yep.
Yeah, okay, thank you. So I have that this is a solution to my function, right? Hopefully everybody understands why this is a solution to the equation. What I'm going to try to do now is to show that this is a solution, right? So this was just a guess. We thought about what functions we know, and we said even then it was difficult, right? So we tried to guess the function whose derivative is twice itself, and it's not an easy exercise to do. So the idea over here is to be able to solve for the function, to find that function based only on the differential equation that we have. Okay, so here's how we're going to do this. We're going to start by writing down the equation. So that's dp over dt is equal to 2 times p. And maybe the first reflex that we would have in a problem like this, if we want to find the original function, is to try to integrate both sides. Right? In which case, we would end up with just the function p on this side, and then on the right-hand side, we would have to integrate 2 times p with respect to t. Right? So we're trying to find the function p, and then on the right-hand side, we end up having to integrate the function p. Not the best strategy, right? Because if I don't know what the function p is to begin with, then why would I end up integrating that function, right? And I don't have a way to actually find the antiderivative of that function. So that means this is not really going to work for a problem over here, because if I'm trying to integrate, that means that I also need to know what the function is. And if I don't know what the function is, then I don't know how to integrate it. So this is not really the best strategy that we could adopt here. Instead, here's what we're going to do. We're going to say dp over dt is equal to 2 times p, right? And what I know is that p is a variable that depends on t, but essentially I have 2 variables. I have the variable p, the variable t, and they're linked to a certain kind of relation. What I'm going to try to do is to try to separate the 2 variables that I have. So I have my variable p, which is the population, my variable t, which is time. And if I could just integrate one side of the equation with respect to p, everything were written in terms of p on one side of the equation, and everything were written in terms of t on the other side, then maybe I could integrate both sides of my equation independently. Maybe that would help, right? So that's the idea over here. That's the logic that we're going to have for solving differential equations. So in this case, what that means is we're going to try to get my, my variable p on one side and my variable t on the other side. And then I'm going to try to integrate independently on both sides. Right? So if I want to get this p on the other side, I'm going to have to divide both sides by p, which means I'm going to get dp over p. And on this side, I'm just going to keep the constant 2. It doesn't matter if I divide by 2 or don't divide by 2, the equation is still going to be the same, and that's just a constant, so it doesn't really matter. So now I'm going to have 2 times dt, which goes on this side. Does everybody understand what I did at this step? Can you please raise your hand if you do not understand? Okay, can everybody that understood? Oh, there's a couple of people that did not understand. So Mark and Aaron, is there something in particular that you are struggling with understanding here?
Could you just repeat what you did?
Okay, so what I'm trying to do is separate the variables, right? This is actually what the name of this technique is, so separating the variables, which means I'm trying to say there's one variable that's p, one variable that's t. I know how to integrate with respect to just one variable, so what I'll try to do is get everything that involves p on one side and everything that involves t on the other side, and that way, hopefully, I'll be able to integrate one side with respect to t and the other side with respect to t, right? So the idea is really to have two independent integrals that I can evaluate each on its own, right? So what I did is on both sides, I multiplied by dt. So I cancel the dt on the left-hand side here, and it goes to the right-hand side here. And on both sides, I divided by p, which means that this one simplifies, and on the other side, I end up with p on the denominator. Is that good?
Yeah.
Okay. And now, because I've separated my variables, I can actually integrate on both sides. Okay. So on the left-hand side, I'm going to have integral of 1 over p. So this is integral of 1 over p dp, which is equal to the integral of 2 with respect to t. Now I can integrate this because this only depends on the variable p, which means I'm going to have ln of absolute value of p. And then on the right-hand side, I'm going to have 2 times t plus a constant. You could technically have the constant of integration on both sides, but you're always going to end up moving the constant of integration of the left onto the right anyway, so you might as well just summarize them into a single constant. I'll elaborate a little bit more on this tomorrow. And then if I want to solve for p, which is what I'm trying to do, right? I'm trying to find the function p. What I'm going to do is cancel out the logarithm on the left-hand side. Does anybody remember how to get rid of the logarithm?
Oh.
Something that will cancel out the logarithm, no? Okay, maybe this will ring a bell. E to the power of ln of x is equal to x, right? So if I put a logarithm on the exponent of e, then that will cancel out. So what I can do is I can put both the left-hand side and the right-hand side on the exponent of e, and then I'll cancel the logarithm that I have on the left-hand side, right? So I'll get e to the ln of p is equal to e to the 2t plus c. Over here, that means that p is equal to e to the 2t. But then here I have plus c. So when I have, again here, e to the power of something plus c is the same as e to the power of the first thing times e to the power of the second thing, right? So in this case, this is the same as e to the power of c. And because this is, so like we know that c can be any constant, it's a constant of integration, so it can take any possible value. That means that e to the c can also take any possible value, so I might as well just label it as another arbitrary constant, right? So what this tells me is that my function p is equal to some constant d times e to the power of 2t. Okay, and p, which is equal to e to the 2t, is exactly the thing that we knew we should find over here, right? So we knew that my function should look something like this. It's just that in this case, I have found an even more general solution that has a constant in front. So that means that this is my general solution to the problem. And then if I want to find a particular solution, I will have to have an initial condition. Does this make sense for everybody? Do I have any questions? No questions. All right. So this is it for today. I would like for you to review the process. If you can do it on your own, that would be ideal, because we're going to be doing this a lot tomorrow. So for tomorrow, you should practice problems number 3 and 4. I'll answer questions at the beginning of class. If you want to go over a little bit what we did today, like this very last part, you can try the first 2 parts of problem number 5, but we're going to do a lot of work on that tomorrow. If that's all, then you're free to go, and I'll see you tomorrow morning. Bye-bye.